Imagine climbing a ladder straight up into the sky. You are, 300 feet in the air, standing inside this swaying steel tube, and you're about to wrench on a massive industrial gearbox that's roughly the size of a minivan.
Yeah, that is not a job for the faint of heart.
Definitely not. Welcome to the deep dive, everybody. Today, we are looking at the massive high-stakes mechanics of wind turbines, exploring the actual nuts and bolts of how we turn moving air into electricity.
Right, and we're breaking down the blueprints of the two major families of wind turbines today. So if you're looking at the stack of sources loaded onto your secure reading tablets, you'll see detailed technical articles, aerodynamic breakdowns, and the history of wind power.
And we are going to synthesize all of that for you.
Exactly. But if we mention a specific design, and you want to look at the actual schematics later, I mean, they're right there waiting for you to go deeper.
So think of this like we are just two coworkers sitting around on a lunch break, talking through how to pull and rebuild an engine. We are skipping the overly complicated jargon, or at least we'll break it down first, and we're really focusing on how these machines physically operate in the real world.
I like that approach. Keep it grounded.
Yeah, and to start us off, I want to pose a question. When you drive down the highway and you see a wind farm, you almost always see the exact same thing, right? A giant white pinwheel standing on a tall stick.
Yep, classic look.
But why does it look like that? And maybe more interestingly, what happens when engineers throw that classic design completely out the window?
Well, before we look at the really experimental, out-of-the-box designs, we kind of have to understand the undisputed heavy champion of wind energy.
The pinwheel.
Right. The industry standard that you see on those highway drives is called the horizontal axis wind turbine. We often just call it HOT for short, right? DWT. The main shaft of the turbine runs horizontally, so it's completely parallel to the ground.
Okay, the classic pinwheel. And while those massive blades get all the attention, because they're what we actually see moving, the real magic, the heavy lifting, happens in that housing at the very top of the tower, just right behind the spinning blades.
Yeah, and engineers call that housing the nacelle. That is a word you are going to see constantly in your reading materials. It's spelled N-A-C-E-L-L-E, the nacelle.
Nacelle, got it. I always like to compare the nacelle to a truck's engine block or its transmission housing.
Well, that's a good way to look at it.
Yeah, if you have ever wrenched on a vehicle or heavy machinery, you know that the housing is where the critical heavy metal components live. Inside the nacelle, you have the main shaft connected directly to the rotor. But here's the thing. Those huge blades spin pretty slowly.
Very slowly, actually.
Right, we were talking maybe 10 to 20 revolutions per minute.
Which is a very slow crawl for machinery. But because those blades are catching so much wind, that slow spinning shaft carries an enormous amount of torque, twisting force.
So it's strong, but slow.
Exactly. And the problem is that the electrical generator sitting behind it needs to spin much, much faster to create electricity efficiently. A generator usually needs to hit, over 1,000 revolutions per minute to magnetically induce a strong electrical current.
Wow, okay. So to get from a slow crawl of 15 RPM up to a blistering 1,500 RPM, you have a massive gearbox in the middle of the nacelle.
Right middle.
It is literally doing the exact opposite of a car's transmission in low gear. Instead of taking fast engine spins and turning them into slow, powerful wheel turns, it takes the slow, powerful turns of the wind blades and uses a sequence of huge gears meshing with smaller gears to step the speed way, way up.
But for any of that torque to be generated in the first place, that giant propeller has to be facing perfectly into the wind. And wind is chaotic, right? It changes direction constantly.
Right.
So if the wind shifts, the entire turbine has to shift with it to catch the air.
So on top of the nacelle, there's a small instrument called an anemometer. An anemometer measures wind speed. And right next to it is a wind vane to measure the wind's direction.
Yep, and the onboard computer reads the data from that anemometer and the wind vane. When it realizes the wind has shifted, it triggers a massive industrial motor.
Which has to move that entire heavy housing.
Exactly. That motor engages with a giant gear ring at the top of the tower, and it slowly rotates the entire nacelle, which, by the way, can weigh hundreds of tons so the blades perfectly face the new wind direction.
That side-to-side rotation is called yaw, rhymes with law. A horizontal axis wind turbine must constantly yaw to track the wind.
It never really stops adjusting.
So the computer finds the wind, the motors yaw this 100-ton nacelle to face it, and now we are ready to catch the air. But looking at the business end of this machine, the math doesn't intuitively make sense to me.
How so?
Well, if the entire goal is catching more wind to make more electricity, Wouldn't a giant desk fan with 10 or 15 blades generate way more power than just three skinny blades?
It seems like adding more surface area would equal more power. I mean, that makes logical sense. But engineering is always this brutal war between efficiency, mechanical stress, and cost. Let's look at the extremes. What if we only use one or two blades?
I'm guessing they'd be really light.
They are incredibly light and cheap to manufacture, and they can actually spin blazingly fast. But high speed is a mechanical nightmare here. They create a ton of noise, and worse, they create asymmetric vibrations.
Oh, because the weight isn't balanced right.
Exactly. As a two-bladed turbine yaws to face a shifting wind, the way the massive weight shifts on the horizontal axis causes this rhythmic pounding. And that pounding basically tears bearings and gearboxes to pieces.
Yikes. So fewer blades mean it spins too fast and shakes itself to death. So we go the other way. What about 4, 5, or 6 blades?
Well, every single time you add a blade, you add a tremendous amount of weight to the rotor. And that requires a much beefier, more expensive tower to hold it up,
Which drives up the cost.
massively. But aerodynamically, because the blades start hitting the turbulent air left behind by the blade in front of them, a four-blade turbine captures only a tiny fraction more energy than a three-blade turbine.
Oh, so they start interfering with each other.
Right. The extra power does not even come close to justifying the massive extra cost. Three blades perfectly balance the physical forces. It provides smooth gyroscopic stability. It limits those destructive vibrations. The rotation speed stays manageable for the gearbox. And, the material cost is justified by the power output.
That makes total sense. And it is worth pointing out right here, servicing these specific machines working on these massive gearboxes inside the nacelle, dealing with the industrial hydraulic systems that adjust the angles of the blades, maintaining the mechanical braking systems that stop the blades during a hurricane. That is serious, heavy-duty mechanical work.
Oh, it really is. And the skills you need to work on these machines translate directly from traditional mechanics,
Yeah.
working on heavy diesel equipment, industrial plant maintenance, pulling wire, or even complex automotive repair. That hands-on mechanical troubleshooting is exactly what the green energy sector needs right now.
Absolutely. You do not need a 4-year college degree to be a wind turbine technician. You need to know how to use tools, how to read mechanical schematics, how to trace a leaking hydraulic line, and, how to safely lock out and tag out a massive gear set so it doesn't move while you work on it.
Those are real-world, high-paying jobs keeping these fleets running.
But as incredible and highly tuned as these horizontal machines are, they carry a massive glaring drawback.
The climb.
The climb. To service that gearbox, to do that mechanical work we just talked about,
Yeah.
a technician has to haul their tools up a ladder or a small service elevator hundreds of feet straight up into the air.
It's just wild to think about.
All the heavy, complex, failure-prone machinery is stuck at the very top of a swaying steel tower. It makes maintenance incredibly difficult, dangerous, and time-consuming. You often need to run a crane just to swap out a broken component.
Which is exactly why engineers started asking, what if we could bring the engine down to the ground?
Now we're talking.
Yeah, and that leads us into the second major family of wind turbines in your reading materials. The vertical axis wind turbine, or VAWT. Instead of the main shaft being horizontal to the ground, the main shaft points straight up to the sky.
Okay, so picture the center pole of a spinning top or like a playground merry-go-round.
That's the exact visual.
Bringing the engine to the shop floor. Because the shaft runs vertically straight down to the base, the heavy gearbox and the generator can sit safely on a concrete pad at ground level. A mechanic can walk right up to the gearbox with a tool cart and work on it just like they'd pull an engine block in a garage.
And beyond that maintenance advantage, because of how they spin on that vertical axis, they are completely omnidirectional. They catch the wind no matter which way it is blowing.
Oh, so they don't need all that yaw machinery.
Right. They never need an anemometer, and they never need a heavy yaw motor. They don't have to rotate the housing to track the wind. They just sit there and spin.
Within this vertical family, though, there are two totally different ways to actually catch the air. And I want to start with the simplest, most rugged, indestructible workhorse of the wind world.
Ah, yes. We are talking about the Savonius turbine. It is spelled Savonius. Savonius. Invented back in the 1920s by an engineer named Sigurd Savonius.
The visual for the Savonius is brilliant because it is so incredibly simple. Imagine you take a standard steel 55-gallon oil drum. You cut it right down the middle lengthwise, so you have two half pipes. Now you offset those two halves a little bit so they form an S shape when you look at them from above.
Right.
And then you put a vertical metal rod down the center. That is a basic Savonius rotor.
The way it generates turning force is just pure, raw physics. It relies entirely on a principle called drag.
Just getting pushed.
Exactly. When the wind blows, it hits the cupped, open side of the drum half, and it also hits the rounded, closed back of the other drum half. The wind pushes much harder on the open cup than it does on the smooth, rounded side. That difference in push engineers call it differential drag, forces the entire structure to spin around the center pole.
Drag is something we all understand intuitively. Have you ever tried to carry a 4x8 sheet of plywood across a yard on a windy day, or, tried to catch a heavy shop door when a sudden gust of wind grabs it?
Oh yeah, it'll pull you right over.
You feel that raw, physical pushing force against the flat surface? That is drag. The Savonius turbine is just capturing that brutal push.
But because it relies purely on being pushed physically by the wind, it comes with a very specific limitation.
Huh.
A drag-based machine can never, ever spin faster than the wind itself.
Makes sense.
If the wind is blowing 10 miles an hour, the absolute fastest the outer edge of that metal drum can move is 10 miles an hour. It simply cannot outrun the force pushing it. So it spins very slowly.
But the trade-off is massive power. Because it has all that surface area catching the wind, it generates a tremendous amount of torque. It is like putting a heavy tractor in first gear. It moves slow, but it provides an almost unstoppable turning force.
And they are nearly indestructible. They do not care if the wind is messy, swirling, or turbulent, which makes them absolutely perfect for the chaotic wind you find in cities, bouncing around buildings, or over rooftops.
And they'll start in almost any wind, right?
Right. Because of that large surface area, they will start spinning in the lightest little breeze.
You actually see these all the time without even realizing it. If you look at the roof of a commercial work van or the top of some warehouse buildings, you will often see these little spinning metal domes. Those are called Flettner ventilators. And inside, they are just tiny Savonius turbines using the wind to turn an exhaust fan.
They are rugged, simple, and perfect for remote jobs, like pumping well water where you need high torque. But as we established with the gearbox discussion earlier, a slow shaft isn't great for making a lot of electricity.
Right. If we want to generate serious electrical current, we need the turbine's central shaft to spin fast. And to spin faster than the wind, we have to completely abandon drag. We have to rely on lift, exactly like the wings of a commercial airplane.
Which brings us to the second major vertical design in the blueprints.
The efficient egg beater.
Yep. The Darius turbine, spelled D-A-R-R-I-E-U-S. Pronounced Darius.
If the Savonius is an oil drum cut in half, the Darius looks exactly like a giant metal egg beater standing on end. It has that central vertical pole, but instead of solid drums, it has 2 or 3 long, thin, flexible blades that bow out in a wide curve and attach at the top and bottom of the pole.
And those bowed blades are shaped exactly like the cross-section of an airplane wing. When the wind moves across them, the curved shape of the blade forces the air to travel faster over one side than the other.
And that creates a pressure difference, right?
Exactly. That speed difference creates a drop in air pressure. The high pressure on one side literally pushes the blade into the low pressure pocket on the other side. That aerodynamic vacuum pulling the blade forward is lift.
And lift is fast.
Very fast. Because lift acts as a multiplier. A Darius turbine can easily spin 3, 4, or even 5 times faster than the wind that is hitting it. That high speed is exactly what you need to run a generator directly, sometimes even eliminating the need for a massive gearbox altogether.
This high-speed efficiency brings up a fundamental law of physics that applies to every single wind turbine, whether it is a horizontal propeller or a vertical egg beater.
Yeah, it is an absolute unbreakable speed limit for wind power, known as the Betz limit. B-E-T-Z.
Yeah.
Pronounced like the word Betz. Named after Albert Betz, a German physicist who figured this out back in 1919.
And what does it say?
The Betz limit states that no wind turbine in the universe can ever capture more than 59.3% of the wind's kinetic energy.
See, that's wild to me. It seems like we should be able to capture 100%. If you have a perfectly designed machine, why can't we extract all the energy from the air?
Well, think about what happens if you actually extracted 100% of the wind's energy. Energy is movement. If you take all the movement out of the air, the wind would come to a complete dead stop right behind the blades.
Oh, and if the air stops moving, it just sits there. It creates a physical wall of static air, like a massive traffic jam.
Exactly. The incoming wind would hit that traffic jam of dead air and just divert completely around the turbine. The blades wouldn't catch anything at all.
That makes so much sense.
The Betz limit is the mathematical perfect balance. You have to extract as much energy as possible by slowing the air down, but you must let it flow through the blades fast enough to make room for the new wind coming in behind it. 59.3% is just the ceiling of physics.
Modern horizontal propellers can get pretty close to that Betz limit, and the Darius, because it uses aerodynamic lift, gets much closer to it than the slow, drag-based Savonius.
Significantly closer. It is highly efficient.
Okay, wait. This is where the math doesn't add up for me. If the vertical Darius is super efficient, uses lift to spin fast enough for a generator, and it keeps all its heavy gearbox machinery on the ground where mechanics can easily and safely work on it without running a crane, why did the horizontal propellers win? Why aren't Darius turbines everywhere?
It comes down to a fatal mechanical flaw in the aerodynamics. Because of the way the physics of lift work on those specific curved vertical blades, a Darius turbine usually cannot start itself.
Wait, really? A heavy wind blows and it just sits there?
It just sits there. Lift entirely depends on the blades moving through the air at a very specific angle of attack. If the turbine is dead stopped, the wind just watches right over the static blades without creating that pressure difference.
So how do you get it going?
To get a Darius spinning, you usually have to draw power from the grid and use the generator as an electric starter motor. You crank the massive machine up to speed manually till the aerodynamics finally catch and the lift takes over.
That is just like having to push start a manual transmission car. You have to get it rolling before you can pop the clutch and let the engine take over.
That is the perfect analogy. Alternatively, engineers will actually attach a small, rugged Savonius turbine directly onto the central shaft inside the Darius.
Oh, combining the two.
Yeah. The brute force drag from the Savonius catches the wind and gets the whole shaft turning, and then once it hits the right RPM, the lift from the Darius blades kicks in and takes the machine up to high speed.
That is incredibly clever engineering, combining the tractor with the sports car. But, engineers never leave a flaw alone. I saw in the articles that the classic egg beater Darius also had a huge problem with metal fatigue.
Yeah, vibration is a real issue.
Right, as those big curved blades spun around the vertical axis, they were constantly moving into and out of the direct wind stream. The mechanical forces on the metal pulsed, pushing, pulling. Over thousands of hours, that rhythmic pulsing caused destructive vibrations that literally shook the steel structure apart.
And fatigue failure is the enemy of all rotating machinery. So engineers started tweaking the formula to smooth out the ride. The first major tweak was the gyromill, sometimes called the H-rotor.
How does that one work?
Instead of long, flexible, curved blades that look like an egg beater, the gyromill uses straight, stiff, vertical airplane wings connected to the center shaft by rigid, horizontal arms. It literally looks like a giant capital letter H spinning around.
Okay, so the rigid arms solved some of the flex, but the gyromill still had that pulsing vibration as the straight blades slammed into the wind stream. Which brings me to one of my favorite design tweaks in the entire reading packet, the helical twist.
Ah, yes. The Gorlov or quiet revolution design.
Yes. Think about the shape of a strand of DNA or a piece of corkscrew macaroni. Engineers took those straight vertical blades of the gyromill and physically twisted them into a spiral wrapping around the central shaft.
It is an incredibly elegant solution to a brutal mechanical problem. With a straight vertical blade, the entire length of the blade hits the wind stream at the exact same millisecond. That creates a massive singular pulse of force on the central shaft.
Damn, just hitting it all at once.
Right. But by giving the blade a helical corkscrew twist, a portion of the blade is always biting into the wind at the perfect aerodynamic angle at any given moment. It takes that massive single pulse and spreads the torque evenly and continuously across the entire 360-degree rotation.
That is what I love about deep diving into these mechanical blueprints. By simply tweaking the geometric shape of the blade, engineers completely smoothed out the destructive vibrations. They solved a complex physical stress problem with pure geometry.
And because these helical turbines run so smoothly and quietly, they're absolutely perfect for turbulent wind environments.
Right. You'll see these helical vertical turbines mounted on the edges of city skyscrapers or urban rooftops, smoothly spinning away in chaotic air that would destroy a traditional horizontal propeller turbine.
It is a textbook example of how adapting a tool to its specific environment completely changes its design. You use a horizontal turbine for clean, massive open-air wind, and a vertical helical turbine for messy urban wind.
Let's wrap this up and look at the mechanical journey we have taken today. We started with the towering horizontal propellers, those highly tuned howls that track the wind perfectly with their yaw motors, balance physics with their three blades, and use massive gearboxes to step up torque into speed.
But they force mechanics to climb hundreds of feet in the air to fix them.
Exactly. Then we brought the heavy engine block down to the ground with the vertical axis turbines. We looked at the rugged, indestructible, push-powered Savonius that lies on drag, invented almost a century ago.
And then we stepped up to the fast, lift-powered Darius egg beater, the rigid gyromills, and those incredibly clever helical designs that smooth out the destructive vibrations with a corkscrew twist.
It is a lot of heavy mechanical ground to cover.
It is. But understanding how these individual machines work in isolation is really just the beginning of the story. Next time, we're going to look at what happens when you group hundreds of these massive machines together. We will be teasing apart the complex grid engineering behind massive wind farms, both rolling across the land and floating out at sea.
I cannot wait to get into the logistics of the offshore platforms. But before we go, I want to leave you with one final thought to mull over. Today, we focused entirely on how a single turbine catches the wind and extracts the energy. But think about the air leaving the turbine.
The wake?
Yeah, every time a blade extracts energy, it doesn't just pass the air along neatly. Remember the Betz Limit traffic jam? It leaves behind a messy, swirling, turbulent wake of slow air. So, if you are an engineer tasked with building a massive wind farm with hundreds of towers, how do you arrange your turbines so they aren't completely stealing each other's wind?
That is a great puzzle to leave off on.
When you step outside and look up at the wind today, try to imagine not just the breeze hitting your face, but the invisible wake you leave behind. Thanks for diving deep with us today. We'll see you next time.